Hello, this is Kara Tierney from Monroe Community College, and in this video we're going to be talking about heat flow. What is heat flow? It's the exchange of thermal energy between a system and its surroundings. And what we use to measure that thermal energy is temperature. I'm sure you've heard of temperature before. When we have heat flow, we always have thermal energy flowing from matter at a higher temperature to matter at a lower temperature. So if we were to take an example of adding ice to a glass of water, the ice is at a lower temperature. This means that its thermal energy is much lower than that of the water. So we have the energy, the heat, flowing from the warmer body of matter, which is the water, into the ice, which is the body of matter with the lower energy level or the lower temperature. So we have heat flowing from the warmer water to the colder ice. How fast that ice is going to warm up depends on its specific heat, which is a physical characteristic of the material. Specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Because it is the amount of energy required for 1 gram, this is a mass-dependent constant. There's another constant that also measures this property that is not mass-dependent, and this is heat capacity. This is the amount of energy needed to raise the temperature of a substance by 1 degree Celsius. So in fact, heat capacity is just mass times our specific heat. The units of these can often tell us how we handle these. So the units of specific heat can often be joules per grams degrees Celsius or joules per mole degrees Celsius. Our heat capacity is usually in joules per degrees Celsius. These can also be given in Kelvin, where we would have something like joules per grams Kelvin. This is actually the same. These two can be used interchangeably. Same with joules per Kelvin. We can use this interchangeably with joules per degrees Celsius. This is because the difference in energy between 1 degree Celsius and 2 degrees Celsius is equal in energy as the difference in energy between 1 Kelvin and 2 Kelvin. The two temperature scales are based on the same difference in energy defining 1 Kelvin and 1 degree Celsius. To find the amount of energy in an associated heat flow, we can calculate it one of two ways. We can calculate it by multiplying mass times specific heat times change in temperature. Or we can find it by multiplying heat capacity by change in temperature. This makes sense because our heat capacity and our mass times the specific heat, these are the same thing. Change in temperature, remember, is equal to our final temperature minus the initial temperature. Let's try using this equation in a problem example. Let's say we have a 1975 penny and it is nearly pure copper and it has a mass of 2.5 grams. A 1975 penny starts at 15.0 degrees Celsius and is dropped into a container of hot water. The copper absorbs 18.6 joules of energy. If the heat capacity of copper is known to be 0.385 joules per gram degrees Celsius, calculate its final temperature. What we're going to do for this is we're going to use one of the two equations that was given to us in that last slide. So we're going to use either Q is equal to m little c delta T or Q is equal to big C delta T. What we use depends on the units of the constant that is given to us for the material. If we look at the units here, we see that we have joules per gram degrees Celsius. That grams right there, that tells us that we need to eventually cancel that out with a mass. So we're going to be using this first equation. Q is equal to m little c delta T. I'm not concerned if you know if little c is specific heat or heat capacity. What I'm concerned with you knowing is when to multiply by m and when not to multiply by m. You know you need to multiply by mass when you have a mass unit given to you in the unit of your constant for that material. So now let's expand this equation. We have this delta T here, but we are asked to find the final temperature. So what I'm going to do is I'm going to plug in what I know to be delta T. So we have Q is equal to MC, and delta T I know is my final minus my initial. So we're just going to put that in here, final temperature minus initial temperature. If you ever have a problem where you're asked to calculate either the final or the initial temperature, you need to plug in final minus initial for your delta T. Now we can plug in our values in order to find our final temperature. So our Q we know is 18.6 joules. We need to decide whether this is a positive value or a negative value. We talked about this when we were talking about exothermic and endothermic processes. So we can decide using the word right before it, absorbs. Absorbs means it's gaining. So gaining energy would be an endothermic process, and this would be a positive number. So we have positive 18.6 joules as our value of Q. Q is always going to be given in joules. You could potentially see it in kilojoules or maybe calories, but it's always a unit of energy. Our mass is going to be the mass of our penny, and that is 2.5 grams. We are given its specific heat, and look, I labeled it wrong. This is specific heat. Obviously, I don't even know the difference between the two names. I just know when to use it. So that's okay with me if you're not sure what it's called, as long as you know how to use that little c or big C. So we have our specific heat, and that is 0.385 joules per gram degrees Celsius. And we're calculating our final temperature, and our initial temperature was given to us as 15.0 degrees Celsius. So now what we're going to do is just some algebra. I'm going to have to keep this together since this is a parentheses with a subtraction inside of it. So we're going to divide our 18.6 joules divided by the 2.5 grams times the 0.385 joules per grams degrees Celsius, and that is equal to our final minus 15 degrees Celsius. When I multiply and divide this all out, that 18.6 divided by 2.5 times 0.385, that will come out to be 19.3. When I cancel out units, my joules cancel out and my grams cancel out. 1 over degrees Celsius, that is equal to degrees Celsius. So we have 19.3 degrees Celsius is equal to our final minus 15.0 degrees Celsius. So our final temperature is equal to the 19.3 degrees Celsius plus the 15 degrees Celsius, and we get 34.3 degrees Celsius. Now let's look at this. Does this make sense? I dropped a copper penny into hot water, and it absorbed energy. The temperature then should be warmer than what it started. Is it warmer? Yes, it has a higher temperature, so that makes sense. We're now going to apply this equation to more complicated problems in our next videos. I'll see you there.